Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar lecture theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar.
So friends, in the previous lecture, we were looking at how fire can act as a structural load. We saw how fire can be characterized in terms of heat release rate, in terms of temperature. We also saw the parametric fire curve where it can consider a growth as well as a decay phase. So in this particular lecture, what we will see is that when does a fire begin to become a concern for structural members. If you recall, we saw that the post flashover situation is when the structural fire safety becomes important, right? The natural fire curve was like this, where there is a growth phase, there is a sustained burning and a decay phase. This we are drawing as T versus T. Here there is a time here which was called flashover, rather an event. Okay. So the pre-flashover, we said life safety operations were important, and in post-flashover, structural safety became important. We also watched a video to see and understand what flashover is and how does it look like in a compartment. Today we will see one more video which has been developed by the underwriters laboratories that compares two types of rooms. One is called a legacy room, one is called a modern room. Okay. In the legacy room, the nature of furniture is natural wood, natural fabric, solid wood, these kind of materials, which is mostly naturally occurring materials. In the modern room, we have synthetic materials or materials which have primarily origin in petrochemicals like particle boards, synthetic fibers and these kind of things. So with this, let us watch this video. Both the rooms have similar energy content in terms of total energy. Ignition is started. Both have similar settings. And again, as it was the case in the previous videos, fire has been initiated at one corner of the room in a waste basket. So initially, the spread of fire will be only through proximity, which is items which are close to the flame, they will catch fire first. Then a hot layer of gas will be formed at the ceiling. This ceiling begins to radiate everywhere, and that is when the entire compartment would catch fire. That event is known as the flashover. So what we will notice here is that room on the right hand side, which is the modern room, it already has begun to give very black smoke, black colored smoke. Okay. Whereas the room on the left, which is a legacy room, it has a more clean burning, so to say. The rate of burning is also different. The size of the fire on the modern room is increasing quite rapidly now, whereas on the legacy side, it is still relatively quite small. Okay. Hot layer of gas and smoke is already very visible on the modern room within just 1.5 minutes, which means that hot layer has already formed and it has already begun radiation to the rest of the room. Whereas on the legacy side, which is the left side, the layer of hot gas is still very small. Okay. In fact, it is not even being visible as leaving out of the compartment. Modern room, you will see that the smoke layer is descending, which means neutral plane is coming down, okay, implying that the reservoir of hot gas has increased in size and also in temperature, indicating a much higher radiation heat flux being emitted and received by the other surfaces which are around, which means what we would expect is that flashover will happen quite fast on the modern room. In fact, it should happen much earlier in the modern room as opposed to the legacy room based on what we are seeing as of now. It is reaching almost 3 minutes. The size of the fire in modern room has become quite large, but it is still not flashed over yet. Whereas legacy room size of fire is still very small. Now you may notice that items which are away from the fire have begun to emit some fumes in response to the heat radiation being received from the top layer. Now these fumes are increasing very rapidly and suddenly this entire room will catch fire. Now this entire room is on fire, which means flashover has happened in the modern room in about 3.5 to 4 minutes. In fact, a bit less than 3 minutes, 3.5 minutes. The size of the fire on the legacy side is still increasing. It is still not large enough where we will have a large layer of smoke. which will eventually cause flashover, whereas the room on the right hand side is completely gone. Okay. And this is the situation for which we have to design structural members, which means after flashover, this is the intensity that the structural members are exposed to. That is where the standard fire curve considers time temperature in the post flashover scenario. Okay. And this kind of scene is what develops. So the time to flashover in the modern room is about 3 minutes 40 seconds, whereas the time to flashover for the legacy room is about 29 minutes 25 seconds. So if we take it as 3 minutes for the modern room and 30 minutes for the legacy room, what we see is that flashover in the modern dwellings that we stay in is happening in as much as 1/10 of the time that it used to happen earlier. In a way, it implies that structural fire safety has become much more important now than it was earlier. Not that it was not important earlier, but the amount of intensity, the amount of time that we have, that is changing quite a bit. If we compare these timelines, okay, it is shown in this graph here. So the shortest time to flashover, this is what we saw visually. Okay. So in the modern system, the shortest time to flashover is around 3 minutes, 3.5 minutes. Legacy timeline, it is around 30 minutes, okay, much more. And pre-flashover is the time when all the life safety operations have to happen. From a structural point of view, what we are interested in is this blue and yellow. Okay. So once we have designed systems, we would want to know in how much time will a structure collapse and given a fire. Right? So what we see from here is that due to the intensity and severity of the fire, structural systems can collapse much earlier in a modern fire as compared to a legacy fire. Okay. So knowing all of this helps us in designing structural members so that we are able to achieve the necessary fire protection. Let us move on to discuss effects of fire on structures. Before we get into detailed temperature calculations, let us look at what are the main effects of fire on structures. So first and foremost is thermal expansion. Here we consider a case of uniform heating, which means say there is a cantilever beam which is unrestrained. We increase the temperature of this entire beam uniformly by delta T. Delta T is the increase in temperature. Due to the increase in temperature, the length increases. Okay? The length increases by L alpha delta T, where L is the original length. Okay? And this is the change in length. Delta L equal to L alpha delta T, where what is alpha? Alpha is the coefficient of thermal expansion or CTE. Okay. This is known for most materials of practical significance. Now in this case, since thermal expansion has been allowed, okay, there will be no additional stress due to the change in temperature. However, if we put a restraint on the other side, which means if we take the same beam and now restrain it on both sides, okay, again we subject it to a uniform increase in temperature of delta T. Now this L alpha delta T, which was the expansion which would have happened if there was no restraint, now it is not allowed. Okay. Hence, in this case, it will lead to thermally induced stress. So we know that the strain, the thermally induced strain, will be simply change in length divided by L. Okay. The change in length is L alpha delta T divided by L. So this is alpha delta T. So, this is the thermal strain, and the stress for a linear elastic material, if we assume it is linear elastic, will be Young's modulus E multiplied by strain. Hence, the thermally induced stress in the restrained case becomes E times alpha delta T. So, that is the additional stress we get purely due to thermal effects. Now, suppose that there were no other considerations and the allowable stress in this beam in terms of compression say is 350 megapascals. Okay. So, from there we can calculate how much is the allowable change in temperature before which this beam will fail. So, delta T acceptable will be Fy. Fy is the yield stress of the material, or in this case steel, divided by E times alpha. Right. So, that gives us the acceptable change in temperature before this system will fail, and this is all happening because we have a restrained system. Now, this restraint will give rise to one more effect, which will be thermally induced buckling. Okay. So, from the basic mechanics, you would recall that for a column which is subjected to an axial load P, okay, and it has a length L, the critical buckling load PCR can be derived using the Euler buckling theory, which comes out to be pi squared EI divided by LE squared, where LE is the effective length it depends on the end conditions. Now, what we know is that this E is a function of temperature. So, again we have E a function of temperature, that we will see how. Okay. But then the critical buckling load is now sigma times A. A is the area of cross section, and sigma we know is this E alpha delta T, right. So, from here again we can calculate T acceptable such that the buckling does not happen purely from thermal effects. So, previous slide we were seeing that this yielding should not happen because of thermal effects. In this slide what we are saying is how buckling can be onset based on thermal effects. Okay. Here lambda is the slenderness ratio. Previous two cases were of uniform heating, which means temperature of the entire cross section and length would be same. So, that kind of situation will be possible for metals, say for steel, which are good conductors of heat. However, for materials like concrete, which are poor conductors of heat, the temperature, say if we are exposing them on one side, the temperature at the bottom face, temperature on the top face can be very different. In fact, for a reinforced concrete cross section like this, if we are saying that the bottom boundary is getting heated up with a temperature T1, the overall temperature distribution can be very highly nonlinear, where this is T1, this may be still T ambient. However, for an idealized case, if we consider linear thermal gradient, which means along the cross section, the thermal gradient looks like this, where this is say T1, this is T2, and this is linear. In such a case, when temperature at one end is more, the other face is less, then again, because one of the fibers will expand more, the other fiber will expand less, it will lead to thermally induced curvature. Okay. And an expression under linear theory can be obtained for thermally induced curvature like so. Now this dt by dy, if it is a linear thermal gradient, it will be a single number, which is the slope of this, and basically this will be T2 minus T1 divided by depth of the beam. So that is what this will be. So this gives to a thermally induced curvature. So the effects we have seen so far are thermal response of the deformation. However, due to temperature, the material properties of the system will also change. So what is shown here in this table is a table 3.1 from Eurocode 212. Okay. It gives few things. On the first column here is temperature. Okay. So 20, 100, this is change in temperature. All right. The column here is Fc theta divided by Fck. Okay. So Fc theta divided by Fck. Fck is the characteristic strength at room temperature, or one may say 20 degrees Celsius, whereas Fc theta is the characteristic strength at temperature theta. We will notice that if you look at this factor, it starts out at 1, which means no change in strength, but when we reach 500 degrees Celsius temperature, the factor becomes 0.6, which means somewhere around between 500 to 560, the concrete will lose half of its strength. Okay. So that is this ratio. And for defining the stress and strain behavior of concrete, we draw the stress versus strain, and this has been parameterized with Fc theta and two levels of strains. Okay. The degradation in the strain is also given, and for concrete it depends on the kind of aggregate also. So this is for siliceous aggregate, this is for calcareous aggregates. Now similar tables are available in Eurocodes as well as in several building codes and also in several textbooks. This table is for concrete. A similar table is available for steel, where one can look at the ratio of Fy theta divided by Fy, where Fy theta is the yield strength at a temperature theta, whereas Fy is the yield strength at room temperature. And in general, all of these properties have a decreasing correlation with temperature, which is that when temperature increases, the strength reduces. Similarly, there will be a relation between E theta divided by E, which is Young's modulus of steel at a temperature theta divided by Young's modulus of steel divided at 20 degrees Celsius or room temperature. So all of these properties follow a trend like this, where with increasing temperature, the amount of property decreases. So if we put all of this together, what is happening is that without fire, there is a certain demand in load. Okay, so this is the demand, and there is a certain threshold, which is the capacity. So there is capacity, and there is demand, and the distance between these two is the margin of safety. Okay. So due to fire, what is happening is the stresses are increasing. Okay. When the stresses and strains increase, implies demand increases. Right. However, because the material properties degrade, this allowable capacity or the threshold, that reduces. Okay. So this in a way reduces the overall margin of safety, and this margin of safety is what we need to be able to calculate so that we are able to design structures under fire. These are some photographs which show the effects of fire on structures. The top two photographs are of steel structures. What is very visible is that there are very large deformations, okay, extremely large deformations. This is because the strength has reduced and thermally induced buckling may have happened, thermally induced additional bending may have happened, right. So there are very large deformations. There is instability, which means this is a case of buckling, okay. So buckling which was not happening at room temperature has happened at a high temperature. And when deformations become very large, these steel type of materials undergo permanent deformations, or sometimes also called permanent plastic deformations. For concrete, what is happening is there are again instability effects, they can happen. There is an additional phenomena called fire induced spalling. Spalling implies that chunks of concrete would chip off out of beam or column. This corresponds to permanent damage, which means damage which cannot be undone. Okay. And obviously large deformations can again happen in concrete. So if we have a structural system, okay, what we are looking at is we have a fire. From this fire, there is a heat transfer to the structural system. Then within the structural system, there is a heat transfer. This is what we need to be able to calculate. Okay. So temperature of fire to temperature of structure is what we need. For steel structures, this is sufficient. For concrete structures, there are additional complications or additional physics that one has to resolve. As we know that concrete is a multi-phase system, you have aggregates, cement matrix, moisture which is in liquid form, and air. Okay. This is at room temperature. At a higher temperature, some of this moisture converts to water vapor. Okay. And we know that when liquid water gets converted to water vapor, its volume increases rapidly. Okay. This causes a lot of increase in pressure internally. This is the increase in pore water pressure of a concrete structure at a higher temperature. Okay. And that can cause additional spalling. And we will see an example where it can cause explosive spalling, which means the column can actually explode under a fire, even though there was no other explosive provided to it, right. This is a simplified view of the heat transfer mechanism. So from the fire, there is a heat transfer to the structural member. So this is our structural member. This transfer of heat is happening through convection and radiation, two primary modes. Conduction also happens a little bit, but it is negligibly small because generally the medium of air is highly non-conductive. Okay. Then there may be boundaries of a structure which are not exposed to fire. Okay. They are exposed to a different temperature, say room temperature. That is where convection and radiation cooling may happen. Inside the structural member, which is generally a solid, the heat transfer happens through conduction. Okay. So there are three modes of heat transfer at play here: convection and radiation from fire to the structural member. Inside the structural member, we have conduction, and then from the structural member to outside, that is convective cooling or radiative cooling. As we said, for concrete structures, there is an additional water vapor transport that one has to look at. Okay. So it again mathematically it can be modeled as a diffusion equation. So there is diffusive mass transfer, but when chunks of concrete begin to spall, okay, then the boundary conditions become updated. Okay. So basically initially this is the heated perimeter of concrete. After say this part has spalled off, the heated perimeter increases. Okay. So this further intensifies the temperature seen by concrete members. So this is an example of an experiment of a slab where, based on the heating, we can see that there is a dry zone and there is a saturated zone. Okay. So when water vaporizes, it will try to expand. When it tries to expand and leave, that is where it introduces tensile stresses in concrete, and we know that tensile concrete is not very good in tension, so it begins to crack from there. And if we are able to break it inside, we will still see liquid water available. So this is the front, water front, which is available. This photograph shows two types of columns. On the left hand side is normal strength concrete, which is lower strength, say up to 40 or 45 megapascals characteristic strength. On the right hand side is high strength concrete, which is very high strength, means strength greater than 50, say 50 megapascals. What is interesting to observe here is that on the normal strength concrete, it will have a higher permeability, which means there will be a higher chance of interconnected pore network being available. So the water vapor which is trying to expand and go out, that is able to escape. When it is able to escape, the extent of spalling is not that severe. When we come to high strength concrete columns, okay, their porosity is very low, permeability is very low. So the water vapor is not able to escape. Hence, it builds a lot of tensile stresses inside the concrete. Okay, and when enough of such pressure has been formed, the concrete column can actually explode. So this has been observed experimentally, as well as this has been observed in several real life fires. Now, an exploding column can be very dangerous for life safety as well as for building safety. For building safety, it is obvious, because this column completely ceases to take load. But from a life safety point of view, many times firefighters are inside the building when the fire has become a full size fire. Okay. So in such a case, if a concrete column would explode, that can put our firefighters at risk, because the proximity suits, etc., although they are designed for thermal exposure, they are not designed for projectile impact. From here, let's discuss what are the design requirements and limit states. So primarily there are three limit states that one will discuss. One is the load carrying capacity. Okay. So it is the total time in which the column or a beam or a slab would fail. Okay. So basically, when the load resistance becomes more than the load effect. As long as it remains more than that, it is okay. Then the second one is integrity. Integrity is that if you have small deflections, but predominantly it is meant for cracks. Okay. So if small fissures or cracks would develop, which will allow hot gases to pass through the other side, okay, that is considered loss of integrity. And the third one is loss of insulation or insulation requirement. Okay. So this is when integrity is still retained, but purely due to thermal conduction from one side of the member to the other side, the temperature increases so much that on the other side of the wall or a wall or a slab, the items or the room can become exposed to a high enough temperature that it can onset another fire. So these are the three fire ratings that one talks about. The first one is applicable to all structural members: beams, columns, slabs, shear walls. Integrity and insulation are applicable primarily to partition members, okay, such as 2D members like walls or slabs. If we again recall the standard fire curve for a moment, we again recall that the standard fire curve represents a post flashover temperature scenario. Okay, and when we say fire rating, now let us define what is fire rating. We have been talking about it, that fire rating is always derived from a standard curve. Right. So let us say if we have a fire rating of 1 hour, fire ratings are defined in terms of time. When we say fire rating is 1 hour, what that means is we take a structural member, put it under the loading condition as it would be in a normal service condition, expose it to the standard fire curve which is shown here. Okay. So if for up to 1 hour the structural member is able to sustain its L, E and I requirements, which is load carrying capacity, insulation and integrity requirements, then it will be said that it has a 1 hour rating. Similarly, we can say what is a fire rating of 2 hours. That is applicable if it can sustain all of its requirements up to 2 hours and like that. Okay. So this is how we define fire ratings in terms of temperature, and these are all derived from standard curve. One of the questions that may arise is that we are defining fire rating based on this standard curve, whereas actually the structure is subjected to this natural fire curve. Okay. Even if for structural members where we are looking at the post flashover scenario, one of the key differences is that standard fire curve is always increasing, so temperature does not decay, whereas in a natural curve there will be a decay in temperature. Okay. So how is this fire rating, which is derived from a standard curve, okay, that is a time, how it is applicable in a real scenario? So that is what leads us to the concept of equivalent fire severity. The first one is called area equivalence. So on the left hand side we have a real fire versus temperature versus time graph. On the right hand side we have a standard time temperature graph. Okay. So if we know that from a real perspective we require this is the total time of burn. Okay. Now we want our structural member to hold up for this total time of burn. So what we do is you calculate the area under this curve, okay, then go up to a time Te, which is the equivalent time. We go up to a time where the area under the standard curve is equal to the area of the real curve. Okay. This is an area equivalence. It is most easy to implement. However, it does not have a physical basis behind it because area of a time temperature curve does not have any physical significance. So you may recall that area of HRR versus time curve, that gives us energy, but area of temperature versus time does not give us anything physically meaningful. So while this can be used, it is not ideal to be used. The next equivalence is maximum temperature equivalence. This is one of the most commonly used ones, okay, and also it is appropriate, and the following is the equivalence. So again we take the real fire curve, we subject the structural member to this real fire curve, okay, and from here we calculate structural temperature. So let us say this is the we are talking about, say, steel member. So this is the steel temperature which we obtain by subjecting it to the real fire curve. Okay. We do the same thing. We in this case we use standard fire curve as an input. So we subject the same member to standard fire curve and calculate its temperature. Okay. So now we have structural temperature from real fire as well as from standard fire. From the real fire exposure, we find out the maximum steel temperature or maximum structural temperature. Okay. We take this to the steel or structural temperature from the standard fire curve, and corresponding to this temperature, which is the maximum in the real case, we find out the temperature on the standard curve and we read out the time from here. So this is the equivalent time. So this is the equivalent time in this case. With this, let us get into some details of temperature calculations, because without temperature calculations it will be difficult for us to do any design related calculations. So here this is a similar slide to a previous one, but here we have written some equations. So this is the heat transfer equation. Okay, so the basic heat transfer, transient heat transfer equation, and then we are showing the boundary conditions in terms of convective radiative boundary condition. First, let us look at heat conduction. So we look at a simple case of heat conduction in one dimension. It is governed by Fourier's law of heat conduction, okay, which says that the heat flux in conduction is directly proportional to the temperature gradient, which is dt by dx. When we remove the proportionality constant K comes in, and K here is the thermal conductivity of the material. It is a material property and it can be measured for different materials. So the slide here shows the derivation of the one dimensional heat equation, transient equation. Okay, I will not read out the steps, but it is simply doing energy balance. Here we have introduced two more properties. One is C, which is the calorific, which is the specific heat of the material, and rho, which is the density of the material. Okay, and cases when this conductivity, specific heat, and density are constant for a material, one can define this ratio alpha equal to K by C times rho, which is the thermal diffusivity So this thermal diffusivity, which is an important material parameter when we are doing 1D heat transfer calculations. So this is the final transient equation that one can solve to obtain temperature distribution across the air. So what is interesting is that this equation enables simple calculations also. Okay, so this derivative we can approximate. We can say this is K times delta T divided by delta X. Okay, so the dt by dx is nothing but when delta x tends to 0, that is the derivative. But under many situations we can simply do this. Okay, and this delta x is nothing but the total length between 2 points. Okay, so this q dot double dash, which is the conductive heat flux, can simply be written as K times delta T by L. Okay, so this is, here we are defining a term called Rk, where Rk is called thermal resistance. It is the ratio of the length or the delta x in which heat transfer is happening divided by K, which is the thermal conductivity. This thermal resistance it acts in a very similar way as electrical resistance. So we have multiple materials, one of length A1, L1 and conductivity K1, one of length L2 and conductivity K2, etc. In this case, we can define thermal resistance for each of them, R1, R2, R3, and this is like resistors connected in series. Okay, so the total R will be simply R1 plus R2 plus R3. So from here, if we know the temperature here, it is easy to calculate temperature at the other end or anywhere in between using the regular electrical resistance methodology. So like this we can do multiple connected materials. can calculate total resistance, and then you can calculate Ti, which is any intermediate temperature can be calculated like this. To do an example, so here a wall is consisting of 230 mm clay brick masonry, 15 mm mortar, plaster, and 12 mm ornamental wooden board. Okay, their thermal conductivities are also given. The outer surface has a constant temperature which is given, okay, and the inner wall temperature is given. So we have to calculate temperature at the intermediate phases. Okay, so in the intermediate phases, that is what we have to calculate. So if we draw this, it is like this. So we have here masonry 230 mm, this is plaster 15 mm, and this is wood, okay, and wood is 12 mm. So looking at this kind of analogy, we know L and K for each. So Ri, which is resistance of ith member, can be calculated, and then you can calculate the R total as the summation, and then you can do the calculation of temperatures. Okay, so please try to do that by yourself. Next we look at convection. Okay, so convection is generally governed by Newton's law of cooling, which states that the convective flux is directly proportional to the difference in the gas temperature and the surface temperature, and in this case the proportionality constant is H, which is also called the convective heat transfer coefficient. Okay, so this is also a property of fluid which can be calculated for different scenarios. And if we continue the electrical resistance analogy, just like earlier we defined L by K as the resistance, the convective resistance can be defined as RH, which is 1 by H. Okay, so if we have a system where conduction is happening here and convection is happening due to the gas outside, the total resistance can be simply calculated as 1 by H plus L by K. Okay, and again we can then calculate the intermediate temperatures, say T1. This is an example, again you can try to do yourself. There is a masonry wall of 230 mm thickness which is exposed to a gas temperature of 400 degrees, alright, and the convective coefficient is given, thermal conductivity is given. We need to find surface temperature of the wall. Okay, so again using the electrical analogy, please try to solve this problem. The third mode of heat conduction is radiation, which happens to be the fastest because it is governed by the Stephen's law, which says that the heat flux is directly proportional to the fourth power of the temperature, and this temperature is always written in absolute terms, which is in Kelvin. In conduction and convection problems, we can use temperatures in degree Celsius or degree Fahrenheit depending on what we require. But for radiation, the temperature must always be put in absolute terms, which is in Kelvin. Okay, so for any surface, there is an incident radiation. This can be a solar radiation also, but a fire can also give this kind of incident radiation. There is some part which is reflected, some part which is internally absorbed, that is the radiative part. Okay, and then some part is emitted from the surface itself, because this also is at a certain temperature. The thing is that any body which is at a temperature above absolute zero, which is 0 Kelvin, it will always be emitting some radiation. Okay, and just like we did for earlier case, a thermal resistance can be defined for this also, HR also. Okay. HR is generally non-linear, but for certain simplified conditions, one may consider it to be a constant also. There are some additional physics involved in radiation. One is that it always follows Huygens principle, which means it travels like like an electromagnetic wave. So if we travel by a distance r, okay, the intensity drops by r squared. Okay, so this is the inverse square law. Then also there is an effect of the angle. Okay, so if someone is straight on versus at an angle, then that is governed by the Lambert cosine law, and these angles give rise to view factors. So if two surfaces which are emitting to each other, they are in front of each other, their view factor, typically denoted as phi, is 1. Otherwise the view factor is different, okay, and this view factor can be calculated. So this is the expression for calculating view factors. However, many books uh, provide view factors for different configurations, okay, which can be directly used instead of carrying out this integral. So for predefined scenarios, these integrations have been calculated, and these are available as tables which can be seen. So again, there is an example. This one I have given a solved example because the calculation of view factors for certain cases is non-trivial. Okay, so we have an uninsulated fire door made of steel, which is uniformly heated to a temperature of 650 during a fire. Okay, so we calculate the maximum incident radiation parallel to the surface 0.5 meter from the door leaf, which is where these are the dimensions. Emissivity is given as 0.9. Okay, so emissivity is again a material parameter. So emissivity equal to 1 corresponds to black body. So black body radiation is a perfect radiation where everything, all the energy is radiated. For all real materials, emissivity is always less than 1, which also sometimes are called grey bodies. Okay, so in this case emissivity is 0.9. So we have this as the given data, and this is the calculation of view factor, and then finally we are able to calculate the maximum incident radiation. Okay, so this incident radiation of 1.4 megawatt per square meter is quite large. So just as a reference, the solar radiation that we receive on earth or that we feel is ranging between 1 to 1.5 kilowatt per square meter. Okay, so this is 1000 times of that. So this is a fairly large incident radiation. So to be able to calculate structural temperatures, we need to understand how different boundary conditions can be applied. Okay, so we know that from fire, the actual what happens is convection and radiation. Okay, but when we solve this heat conduction equation, it needs to be given this information. So the most realistic type of boundary condition that typically should be used in a software is called this Robin or mixed type boundary condition, where the heat flux, incident heat flux on the surface is a combination of two parts. This is the convection part, Tg minus Ts, and this is the radiation part. Okay, so we need a convective radiative boundary condition on the surface. That is the most ideal. In certain cases, it may be computationally not very easy to do. Then the second best option is to give a Neumann boundary condition or a flux boundary condition. So just like in the previous example, we calculated the heat flux which is incident. So this heat flux after calculation can be taken and directly applied as a boundary condition on the wall, on the surface of the wall. Okay, so this is the second possibility. The third possibility is to directly give surface temperature of on the structure. Okay. So this is from a calculation point of view, this is the easiest. However, from a realistic point of view, this is not ideal, okay, because generally temperature is not given directly on the wall surface or on a structural member surface. What we know is gas temperature. Okay. So from this perspective, most ideal boundary condition is this mixed boundary condition where we know the gas temperature and surface temperatures are calculated. Okay. Second best option is this flux condition where we first calculate the flux and then give it as an input. Third possibility is a Dirichlet or a temperature condition where temperature of the surface is directly specified. So to summarize, what we have seen today in this lecture is whether fire is a concern for structural systems. It is, from the following perspectives: that structural safety becomes important post flashover, and in most of the modern dwellings the time to flashover has been reducing. Okay. Second, what are the effects of fire on structures? One is obviously thermal expansion and curvature. So this is deformations originating out of change in temperature. And second is degradation of material properties. So these two things combined reduce the margin of safety, as we saw. Then we looked at the structural fire ratings. Okay. Fire ratings will be of three kinds. One of them is strength related fire rating, L. One of them is integrity, one of them is insulation. Okay. For structural members, all three apply. Integrity and insulation are primarily applicable for 2D members, whereas structural ratings are applicable for any load bearing member, whether it is 2D or 1D, which means whether it is a wall or a slab, which is 2D, or whether it is a beam or column, which is 1D. We looked at an equivalent fire severity concept, which links the fire ratings which are derived from standard fire curve to a real fire exposure. Okay. There were a couple of things that we saw. One was area equivalence and one is temperature equivalence. Then we saw how temperature calculations can be done in structural members. We saw simple ways to calculate conduction and convection and radiation, and we also saw that if one has to do a more complicated analysis, what kind of boundary conditions can be used for thermal analysis. So this is all for this lecture.